So simple machines, we're in section 13.2. Our objectives, we want to describe the 6 different types of simple machines. We want to list the 2 principal parts of all the levers that we deal with, and we want to talk about how that inclined plane is actually helping to change the force required to do work. And we want to list examples of compound machines and then simple machines that they're made up of, okay? Lots of different compound machines, we're just going to do some of those. All right, so a lever is a rigid arm that turns around a fixed point called a fulcrum. So these are the 2 components that we have. We have the rigid arm, okay, that's one part of the lever, and then the other part is the fulcrum. Okay, so those are the 2 components, and you are going to increase your mechanical advantage by either increasing your effort arm, or you could decrease your resistance arm. Okay. All right, now a first, second, and third class levers are the types we're going to be talking about here right now. Okay, first class and third. Now, the first and second class levers have mechanical advantages that are greater than 1. The third class lever has a mechanical advantage that's less than 1. Okay. So as we talk about these first 2 parts work for first and second class levers, but your third class lever is going to work a little bit differently. Okay, so let's talk about our first class lever first. Let's talk about what we have. We want to think, when we're thinking about all the different types of levers, we want to think about what's in the middle. Because if you can identify what's in the middle and identify it with each class lever, then you'll be able to figure out which it is. Now, the fulcrum is in the middle of a first class lever. Your resistance, also known as your output force, is on one side, and your effort, also known as your input force, is on the other side. Now, it's a little harder to translate this to a real-world example sometimes because it doesn't look as simple as this nice piece of wood with a big triangle fulcrum in the middle. Let's look at this hammer, for instance. We know that there's a nail right here that the hammer is trying to get out. That is resisting the hammer, right? So that is our resistance. And so our resistance arm is this tiny little distance between our nail and where the hammer is going to be rotating around the axis. Now the effort arm is this arm here, right? As you are looking at where my handle is being pulled on. That's the effort, right? So my effort is up there. My fulcrum is in the middle. My resistance is right there. Now, if you want to see how much of a mechanical advantage this has, then you would want to basically look at the distance that you have here, and you want to compare that to the distance that you have over here. So how many of these are actually present in the effort, right, arm? So I've got 1, 2, 3, 4, 5, 6, 7, 8 maybe. So maybe my mechanical advantage is 8 because I've got 8 of those distances in my effort arm compared to my resistance arm. And so that can be really helpful to have an 8 times more powerful force pulling that nail out than you would have if you just try to pull it out with your hand. So that can be pretty impressively different, right? So let's look at it with regard to these meter sticks that we've set up. Okay, so what we do first of all is we set up, and we have a 500-gram weight or 500-gram mass, and when we take the weight of that 500-gram mass, we'll see that it's about 5 newtons, okay, 4.9 newtons. So we're going to set that up, and that's going to be our resistance over there, and then we want to create an effort over here. And then we want to see how much is this lever actually helping us? Okay, so I'm going to kind of scooch this thing over to the edge so I can pull the spring scale down and get a feeling for it. So we want the distance to be about the same from both of these sides, right? And if they're about the same, we should see that the effort I have to put into this should lift that weight, but that should be the exact same effort. All I'm doing is changing the direction. Instead of lifting up, I'm pulling down, which is going to be helpful for gravity's sake, right? So if I pull on that, you're going to see that I have an effort of about 5 newtons, which is exactly what that is. So there's 2 ways that I can make this thing a more efficient lever. One is by increasing my effort arm distance. Well, I mean, I'm basically maxed out to my effort arm distance if I keep them in the middle. Or I can decrease my resistance, okay? Now, I could make my effort arm really long, and I could just move this fulcrum all the way over here. But let's just keep the fulcrum in place right now. Let's keep it in the middle. And let's move our distance of our resistance in. In fact, let's halve it about, okay? So it's about there. So basically cut it in half. So if we cut our distance in half, then we should be cutting our effort in half as well, okay? So I decrease my resistance distance. Therefore, if I pull on this now from the same spot, oh my goodness, it's so much easier, all right? It's only about 2 to 3, somewhere in there. So I've reduced it by half. If I reduce it by half again, okay, then it should be even easier, right? And so now I can pull on it, and wow, it's super easy. Compared to like maybe 1, 1.5, it's barely anything. And if I keep doing that, the closer you can put your fulcrum to the resistance, the easier it's going to be to lift this thing. There was a quote, I forget who it was that said it, but at one point somebody said, give me a lever long enough and I can move the earth, right? I can move the world. Because you can kind of just imagine, you know, if you could do this. But if you somehow had this fulcrum fixed in space and you had a lever, you know, millions of miles long, you'd be like, pull on one side, and all of a sudden the earth moves. Now it moved very, very small, right? Because you can see, look at the distance that I'm moving this. My hand has to go pretty significantly far up and down, and this is only lifting up like 1 inch, right? And my hand, well, I guess maybe it's like 2 or 3 inches maybe. My hand is going like 12 inches, right? So you can imagine if I had a really, really, really long lever, I'd be pulling on that thing a little bit. It would just barely budge the earth. But the idea is that you could have, if you could, that's just kind of a silly example. If you have a longer lever, the bigger the effort arm, then you're going to end up having a lot of your effort force multiplied. Okay, so that's a first-class lever. So let's see what kind of real examples we have of a first-class lever. Well, a pair of scissors has got a fulcrum in the middle. Okay, my effort is where my hand is, right? Over here, excuse me, and my resistance is right where I'm trying to cut. Hopefully I'm not trying to cut my fingers, right? But that's what I've got there is a first-class lever. Another first-class lever, okay, a pair of pliers. Again, the fulcrum is in the middle, and I'm holding on to something right there, right? That's the resistance, and my hand is gripping onto it and putting the effort in on the other side of that. All right, so let's look at our second-class levers and see what kind of things we have there. So if we see our second-class lever here, we can see that the fulcrum is on one end. And again, I said pay attention to what's in the middle. The resistance is in the middle, okay? Resistance is in the middle. Now, my effort is now on the other end of my fulcrum. Now, you can see this wheelbarrow is a great example of this. The center of gravity of this big old pile of whatever it is, it's right here, okay? That's the center of gravity. That's the resistance. The earth is pulling that thing down. The fulcrum is going to be down here where the wheel is at, right? So that's got to be our fulcrum. So we've got a fulcrum. We've got the resistance, which is our weight. And then where do we pull up on the handles? Well, we pull up on the handles over here. And so that's my effort. And so you can see with the wheelbarrow, we have a good example of the second-class lever. So let's see what that looks like with these meter sticks. So with the meter sticks, let's go ahead and put the fulcrum on one end. Okay. And then now we want to have our resistance in the middle, right? So we've got to put our resistance in here. And our effort has got to be on the other end opposite of the fulcrum. And so now we can take that 5 Newton weight, or 500 gram mass. And if I pull on this, right now we're at about 2. So it's doing pretty good. It's making it pretty easy on me. What happens, that's a long effort arm, right? And a short resistance arm. Let's make my resistance arm as long as my effort arm. So now it should be very similar to what it was when I just lifted it by itself, right? And so, yep, sure enough, that's about 5. Okay. So if I get this all the way up to the very, very edge where the fulcrum's at, do you predict it's going to be easier or harder? My effort arm is still really long. My resistance arm is now definitely shorter. And I should pull it in nice and close there. And now as I pull on it, I'm getting not even to 1, right? So not even 1 Newton of my effort is lifting 5 Newtons of that weight. Excuse me. Okay, so now I can take that effort arm and I can bring it all the way in here. What do you predict is going to happen then? Well, again, I'm close to that weight. And so once again, yeah, I can see that it's up there, very close to that 5 Newtons again. So you can see a second class lever where the resistance is in the middle and the effort is on the end and the fulcrum is on the other end. Now let's look at some examples. A real world example might be something like this bottle opener. Okay, so the bottle opener has a little lip on it here, which is where it's going to pull up on it. So that's the resistance. The fulcrum is the part that moves the least. Okay, think about the fulcrum as the part that moves the least when you are going back and forth. And then my effort is down here, right? So I'm moving my effort on one end, the fulcrum is on the other end, and the bottle top opener is right here in the middle, and that's the resistance. So the resistance is in between the fulcrum and my effort, and that pops that open. Okay, so that would be a great example of a second class lever is a bottle opener. Okay, let's look at another example. Let's look at a third class lever. All right, so our third class lever has a fulcrum on the end, and then instead of the resistance in the middle, now my effort's in the middle, and then the resistance is on the end. Now again, remember I said this one's going to have a mechanical advantage that's less than 1. Okay, so mechanical advantage less than 1. And why in the world would this be a good thing for us? Well, if you think about our arm, here's our arm. The fulcrum is the elbow. Our bicep muscle, all right, it has an attachment to our bone. Okay, so there's our bone. It has an attachment to our bone right about there, let's say, and then our resistance is over here. Okay, that's where the weight's at, right? So I have an effort in the middle. And it's not a very efficient machine for reducing your effort. But what it does is it gives you unique movement opportunities and unique ranges of motion. For instance, let's look at, let's say I'm trying to do some golfing. Ooh, nice big long arms here. And I've got a golf club. And I'm going to be swinging that golf club. Now, when you swing that golf club, you have got a large radius that's moving around, right? So I'm putting effort in the middle here. Okay, this is the golf club. The resistance is down here. And then my fulcrum is moving the least. It's over here. And so my effort is in the middle. But I'm going to get a large arc on this swing. And so that's going to give me a bigger radius. of my swing, and that's going to generate more velocity. So I'm going to have a lot more speed when I hit that golf ball because I have this large arc and I'm applying my effort inside, but I'm getting a whole lot of bang for my buck because I have this long arm here. And so I can still have a really long resistance arm, and that can give me a really good bang for my buck if I can generate that speed. Now it gives me advantage in terms of the motion, okay, that I would have. And it kind of seems strange, but that definitely is a benefit. Now, where do we see that? I already showed you that golf club, but imagine that we had something like if you were doing like a fishing rod, right? Same kind of thing. You're pulling up on it, fulcrum's down here, your effort's in the middle, resistance is out here. Bat, same kind of thing, right? You're going to put some effort in the middle, fulcrum is at the bottom of the bat, and then your resistance when it hits is going to be up there. So you're getting this advantage over and over again in a third class lever. If I have a broom, I can move my hand a little bit and I get my resistance distance is huge, right? So I can move my hand this much, but again, I swept that much of the floor, right? And so fulcrum's up here, and then my effort's down here, and then my resistance at the bottom of the broom where those bristles are touching the floor, that's a big arc. So I'm getting a lot of advantage in the distance being covered, even though I'm having to put more effort in here than I've got a lot of resistance over there. So what does that look like here? Well, we know our fulcrum is going to be at one end, but now our resistance is going to be over here at the end, and my effort is going to have to be in the middle. Okay, oops, let's turn that around. Okay, so now this is kind of interesting. Now, if I go out here and I keep my effort arm and my resistance arm about the same, then I should see that it's kind of close, but it's actually already more than 5 newtons. Why? Well, now I'm lifting the weight of the meter stick as well, right? And so I've actually got to put more into it. Now, the further I go inside, the more I'm going. Like here, I'm at 8 newtons. Come in here. Here, I'm at 10 newtons, right? Come over here. Here, I'm at 19 newtons, okay? So the further I go in, the more I'm attached inside this, the more effort I've got to put into it to lift that little weight. So when you're lifting those weights, right, and you're trying to lift those weights, and your bicep muscle is attached right here and it's trying to pull it up, think about how much force is your bicep muscle is having to put to lift the weight that's there, because that distance is pretty significant compared to that distance, right? And so you're like poor bicep muscle, right? It's doing a lot of work there. All right, so that is a third class lever. Now, what other kind of third class levers do we have? Well, if you think of something like these are test tube clamps, you've got resistance here, and then you've got the fulcrum here, and you've got the place where your hand is right there. The tweezers would be the same, all right? Tweezers would have the same thing. Your effort is in the middle, and so you can see that the resistance is where it's holding on to something, and then you've got your resistance in the middle. Tweezers would be the same there. Fingernail clippers. Fingernail clippers are an interesting little set of machines. Probably want to talk about this when we talk about compound machines, right? But you got this really unique layout for your fingernail clippers. And you think about it, you've got the clip part, right? So this is the clip part. Now, we'll talk about what the little blades are over here. But you've got the part that moves the least has got to be the fulcrum, right? So that's got to be down there. And you've got something has got to be pushing on it to make them close, right? And it's got to be there. So that's got to be your effort. And then there's got to be some resistance there, right? So this has got to be, your resistance has got to be there. And so if your effort's in the middle, that's a third class lever, isn't it? All right, so we have a third class lever right here. Now, if you pay attention to the fingernail clippers, you look at them closely, you've got this little this little thing that goes through here, right? And you've got the little piece that you push on, right? So this is the part that you push on. So you're pushing on this, and one of your fingers is like up here, and the other, like thumb is down there, right? So now I've got another little thing here, all right? So I have this machine, those two little guys there, and now I've got another part. This is now where my effort's at, and I can see that I'm going to be moving this down, but this part up here isn't moving much at all, right? So if you've looked at that closely, you can see that it's lifting it, right? It's kind of got like a lift, and so this is actually going to be a fulcrum in this case, and then this is going to be where my resistance is. So if you think about it, you've got this first class lever here. Whoa, S backwards. Types of machines here. It's made up of that first class lever at the top because you've got the effort that you're pushing down on it, right? And then it's got a fulcrum right here in the little middle part with the resistance here. And as you push down on it, it lifts this little guy up and that closes this guy down. But these guys down here, remember, those are the third class levers because you have a fulcrum. That's the little part that doesn't move at all down there. And then you've got your resistance here. And then the effort is going to be applied right here. So you've got these multiple little machines going on, and it's kind of cool to see that you've got these third class levers, and trying to write upside down is challenging at best. Okay, so that's a pair of nail clippers. All right, and that's actually called a compound machine. We'll talk about compound machines a little bit more here in a second, but let's talk about a couple other types of machines that we have. These are simple machines. And so let's look at, and this is just a table that I want you to be able to kind of, have the ability to create a picture of each of these, right? So you can kind of think of, like a crowbar, okay? You could draw that for the second class lever. You could try to draw a bottle opener, right? And so have fun trying to get creative on drawing some things, right? On a third class lever, you could do the broom. That's a real easy one to draw. But you'd want to say, hey, here's oh my goodness, my person is really scary. But you try to draw a picture of each of those and have an example of those so that we can get a feeling. Now, each of these would need to be labeled. Okay, for the test, we'd want you to be able to label like that's where the resistance is, and my effort is here, my fulcrum is here. Oops, that's not F, that's an E. And then, like on this one, we'd want you to be, let's say, okay, this is where my effort's at, my resistance is in the middle, and my fulcrum is at the end. And on the first class lever, we'd want to be like, oh, okay, well, if this is a crowbar, maybe I'm pulling here, and so this is my effort. My fulcrum's in the middle, and my resistance is here, right? So we could do a couple different types of examples here. And remember that the mechanical advantage of the first and second class levers are going to be greater than 1, and that you're going to end up increasing them by increasing your effort distance, right? And the mechanical advantage of the third class lever is going to be less than 1. And the reason we use it is to get basically an increase of effort effect, right? The distance, effort distance effect. So you're going to get this, resistance distance effect. Your effort does a little bit and your resistance does a lot. I don't know how you want to say that. Effort distance effect, I think, is probably making sense in my mind. But the resistance distance is going to be a greater distance for the small amount of effort that we put in. Effort distance we put in. All right, so be able to draw those pictures and have examples of those. Now let's look at a wheel and axle. Okay, the wheel and axle, we've got a steering wheel might be a good example, or the wheel in your car might be a good example. You're going to increase your mechanical advantage by increasing the diameter of your effort. Okay, so in this particular example, if this is a car wheel, then I've got a distance from here to here is going to be my resistance distance, right? If I have a car wheel, then my effort with the machine of the car engine is applying a small amount of distance there. So my effort distance is actually small. And so in a car, you actually have a mechanical advantage of that wheel. Okay, the driving wheel is actually having a mechanical advantage of less than 1. But your steering wheel will have a mechanical advantage greater than 1. Okay, so this is the drive. How about the road wheel? That way it makes more sense. The road wheel, mechanical advantage less than 1. The steering wheel, mechanical advantage greater than 1. If I have a really big if I have a really big wheel, if you've ever been in a tractor trailer, you notice those wheels are bigger than the ones in cars, then that helps me to have more of my effort applied to that tiny axle, which helps to drive and steer my car, okay, or my tractor trailer. So the bigger the wheel that you're steering with, the easier it's going to be to turn. Buses are going to be the same way, right? They have those bigger wheels. But on the car, you're actually doing something a little bit different, okay? Now, when we get to the video, there's going to be a video that I'm going to have you guys watch at the end. If you guys have ever paid attention to train wheels are a little bit different. Train wheels, if you guys have ever paid attention, they've got this little gear arm that moves around in a circle, right? And it kind of moves that wheel around in a circle. And so that gear arm is where the effort's being applied. As the effort's actually being applied along that far distance. Okay, so the effort arm is actually pretty long on a train wheel. And then, the resistance is really down here where the road is meeting the track is meeting the wheel, really. So the effort and the resistance are going to be pretty similar on a train wheel. But, you do also have an axis, right? But that axle is probably not doing as much because it's just kind of there to let it spin around. So you do have a mechanical advantage there. But a train wheel is going to have a slightly better mechanical advantage than a car wheel because your car has the axle and the drivetrain right in the middle, but your train is going to have that drivetrain going to be out toward the edges there. At least that's old school trains. I don't know if those new school trains work the same way. I'm just picturing the old school trains. All right, so that's a wheel and axle. Now, let's look at a typical example that we'd see in our everyday life of a wheel and axle, and that would be like a wrench, okay? If we have a wrench, you're turning that wrench, right? And what's happening is you are applying an effort over a long distance, and that bolt or that nut is applying a resistance, and it's going to be a small little diameter resistance, but it's going to be a long diameter of that pull. And so you're going to be pulling a much bigger distance. And so this is going to be high mechanical advantage. And the longer the wrench, the more mechanical advantage you're going to have, right? And so a wrench is a great example of a wheel and axle, even though you might not normally think of this as a wheel, right? But it is. It's a wheel and axle, and that's the kind of machine we have there. Okay, so let's look at a pulley. Now, pulleys are really cool machines. And how do you increase mechanical advantage? You're going to increase by increasing the number of pulleys. Kind of sounds funny, but what we do is we create a block and tackle system. Okay, the block and tackle system, I just wrote right in the middle of that. is going to be something that basically connects multiple pulleys together. So you start with the smaller pulleys on the inside, and then as you go further to the outside, you get bigger and bigger wheels. Now what happens is this is still attached, just like the pulley you have up here. It's still attached to some sort of beam, let's say. But on this one, you're lifting the bucket up, and the good thing about this pulley, even though it doesn't seem to give me much mechanical advantage, it has the exact same amount of effort and input, input force as it does output force or resistance force. It does let me change direction. So the bucket is going up while I pull down. So that means gravity kind of gets to help me out as my gravity's pulling my arms down, right? So it's going to help that out a little bit. So it's helpful, but it's not as helpful as a block and tackle system. Let's say I start with a rope that's attached there, and I start to make a little rope that goes around each of these little pulleys. Now, if I want to know the mechanical advantage of a pulley system, my job is to count the number of ropes that go through the middle, okay? And you're not allowed to count the rope that you pull down. You can count ropes that you pull up, but you can't count ropes that you pull down. So let's count the number of ropes. 1, 2, 3, 4, 5, 6. So my mechanical advantage of this pulley system is a 6. All right, that gives me a 6 times advantage to actually pulling on something. So if I had a piano, the piano, let's say, is attached to this part down here, right? And you're trying to lift a piano up to the first or second floor or something, right? If that piano weighed, 1,000 pounds, then, or about 1,000 newtons, then my pull on here would be 1/6 of that. Okay, so I would only have to be pulling, what's 1/6 of 1,000? Less than 200, right? I'd be pulling less than 200 down in this direction because my mechanical advantage is going to give me 6 times the strength. Now, what's the disadvantage there? Well, I've got to pull on this thing a lot, right? I'm going to make this example easier. I'm going to say 6,000 newtons pulling down, 1,000 newtons that you're actually having to pull. Pulling down 1,000 newtons, and it's going to lift up 6,000 newtons. But what's the disadvantage? Well, for every 1 meter that I lift this thing up, I have to pull down 6 meters. Okay, so you'll notice that it's an equal trade-off, right? I might be getting 6 times the strength out of it, but I'm having to pull down 6 times the length. And that's what happens when you have mechanical advantage with machines. You're always going to sacrifice effort for distance, all right? So you're going to have to give up some distance if you want to get better effort. All right, so that's a pulley. A lot of fun to play with pulleys. All right, then we have the inclined planes. It's a whole family. We have 3 different types of inclined planes that we're going to talk about. And the first one is a ramp, right? And it's a really basic, simple example. But basically, you have to increase your effort distance, their input distance, in order to increase your mechanical advantage. All right, so if you want to get it easier to do, if this is 6 meters I travel, and I make myself go up 2 meters, then that mechanical advantage would be 3, right? So I've got to increase this increase this distance. So I could, if I wanted to make this an even easier ramp to push something up, I would have to decrease and make a less steep slope, and that would make it even easier to push it up. Okay. All right, so that's the ramp. Now, you also have a wedge. And a wedge is kind of like having 2 inclined planes kind of glued together. Excuse me. And so your 2 wedges here, you can kind of see almost like they're stuck together in the middle, right? That's right, 2 wedges, 2 inclined planes kind of stuck together. And a knife would be a good example of this, or an axe would be a good example of this. And the idea kind of works the same as an inclined plane. Like this little guy has got to cover a certain amount of distance as it moves through the wedge. And the sharper this knife is, that's basically the skinnier the blade is, or you could say the longer the distance it has to travel, then the easier it's going to cut. Right? So if you have an axe that has a wedge that's like that, it's not going to cut nearly as well as an axe that has a wedge like that. Okay? So this is a steeper, this is a steeper slope according to the middle, right, than this one. And so the one that has the less steep slope is going to work much better. All right, so we can increase the mechanical advantage by using thinner wedges. All right, and then we have the screw. Now, a screw is another type of inclined plane, and we don't think of a screw as an inclined plane, but really it is. It's an inclined plane that's wrapped around a cylinder, okay? And if you want to increase the mechanical advantage of this, then you're going to make the threads even closer. So let's just see how this works. It's one thing to see a picture, but it's another thing to see it happen kind of live. So here is your inclined plane, and it just looks like a ramp, right? It's just a little ramp. And if I take that, and I have a cylinder, and I just start wrapping that that inclined plane around the cylinder, you're going to see that, yes, indeed, we have these little threads that are starting to show up, okay, on this cylinder, okay? So you can see those threads, just like the threads of a screw, right? And so that's basically exactly what a screw is. It's just an inclined plane wrapped around a cylinder, and it's going to give you a great mechanical advantage, okay? That if you want to have even better mechanical advantage, you just have to put those threads even closer together, which basically is the same thing as saying you're going to make that inclined plane longer, which means that the slope is going to be less. And if you think about, taking a hammer and punching a nail through the wood, it's a lot of effort, even though it might not be hard for you to do it because the hammer has extra weight on it, right? But that extra effort compared to just going, right? That little thing is going to slowly get that screw in, and it's going to take less effort, even though it's going to take a lot longer because you've got to go through a longer distance. The amount of work is going to be the same, perhaps, but the actual amount of effort is going to be less by using that screw. That would be the same thing as you screw something into wood. All right, so let's look at our simple machines. We have got 6 simple machines here, 6 types. Remember that we have 3 types of levers, okay? 3 different types of levers. And then we have the wheel and axle, pulley, screw, wedge, and inclined plane. So those are the simple machines that we have to know. And again, you should be able to draw them and give examples of each of these in order to do the test. So what kind of other things do we have? Like, for instance, the screw, the drill, a jar lid, a spiral staircase, pulleys. Where do we see those? On mini blinds and flagpoles and drapes. Axes, we already talked about wedges with axes, knives. But nails and forks and things like that. The scissors is a good example of where you'd see a wedge as well, right? In fact, let's talk about that because scissors are a compound machine. Compound machines are machines made of more than one simple machine. A car jack is one example. Wondering what kind of car jack we're talking about. These kind of look like this, and they have a little device that is like a crank that you can turn that crank around, and then it's connected to a screw mechanism in here, which basically as you turn that crank, you're going to move that screw, and so that's going to move that car jack up. So it's a compound machine. It's made up of a few different things, lever arms and screws and things like that. But let's talk about just something as simple as scissors, right? So on a scissor, you have a pair of scissors, you have a few different simple machines. You've got the first-class levers, right? You've got the 2 first-class levers that are there, but you also have that wedge, right, or the inclined plane that's going to act as that blade. And so you've got some compound machine there made up of simple machines. This is a compound machine, right, the pliers, because they're made up of 2 first-class levers. And if you think about it, each of these little teeth that are in here, those are tiny little wedges that are helping to grab onto things. You've got the compound machine we already talked about with the fingernail clippers, right? That's a good compound machine. So we've got different compound machines that are very helpful in the different things that we are doing. Let's look at some others. The wheelbarrow we already talked about is a second class lever, but it has a wheel and axle as well. So that's a compound machine. Pencil sharpener. It's got the lever arm that you turn and a wheel and axle inside that moves that whole case, and it's got a whole bunch of wedges inside so that when that pencil gets in there, those wedges are cutting up that pencil into smaller shavings. You've got a crane that has pulleys, levers, wheel and axle. You've got bulldozers, clippers, escalators. These are all different types of compound machines. So compound machines have more than one machine in them. So now let's see if you can identify what some of these things are. Honestly, I have trouble identifying what that second one is. So the Allen wrench, that one, even though it seems like it might look like a crowbar, it's actually that wheel and axle, right? The wrenches are wheel and axle situations, right? Because you put that wrench inside and then you're going to move that outside lever around. And so that's going to be a wheel and axle. The tire lever, this little part right here hooks into the rubber of the tire you're trying to pull out. And then you're going to, so that's going to be the resistance, right? And then it kind of spins around, right? But that spinning around part is part of the fulcrum. And of course, your effort is over here. And so this is actually going to be a first class lever, the way it's being used in this case. And the air pump is the one that I think is a great example. We know it's a machine, right? It's helping us to make a job easier, right? It's making work easier. But if you think about it, you've got this chamber and it's got a cylinder, right? And it's got a little valve in it, and you're pushing the air through it, right? But I mean, this looks like a wheel and axle, but it's not operating like a wheel and axle in terms of spinning. You're putting force down in one area, and it distributes the force through this entire area. So I guess in some ways it kind of acts like a wheel and axle. But I'm not really sure what simple machine or compound machine this one actually is in terms of what we've been talking about. I think it's kind of a quandary to me. I don't know if it is a quandary to you or not. Okay, so now we've talked about machines. Let's look at our objectives. Did we learn what we set out to learn? Can we describe the 6 different types of simple machines? Yes. Can we list the 2 principal parts of all levers? Remember, we have the rigid arm, and then we have the fulcrum. Describe how the inclined plane changes the force required to do work. It increases the distance upon which that force has to be applied. And can we list some examples of compound machines and the simple machines that are made of? Sure we can. All right, we've done the scissors, a pair of scissors, we've done the pliers, we've done the pencil sharpener, we've done the what am I trying to say? The nail clippers. We've done lots of different ones. So, all right, so that covers what we wanted to talk about today. Hope you enjoyed learning about machines.